All right, so we'll move on to uncertainty. The uncertainty just tells you how well you know a value. It depends on the method of measurement, not just the tool that you use, so that very much affects how well you know the measured value. Like let's say you're trying to measure, I don't know, the width of a piece of paper. If you use a ruler to measure the width of a piece of paper, then your uncertainty is going to be a lot higher than if you were to use, say, a vernier caliper like we use in the lab. So the uncertainty tells you how well you know a value. And we express it in this way. Say, for example, I have a measurement for x that's equal to 4.5, and I have an uncertainty of 0.2. X potentially has a value anywhere from 4.3 all the way up to 4.7. This uncertainty tells us a range, and at least in this case, there is equal probability for the measurement to have a value that lies within this range. Sometimes we might express uncertainty in a different way, and we do this in the lab, but it's important here too. Sometimes, like for example, we might express it like this, 4.5 plus 0.2. And that means that the value has a range anywhere from 4.5 to 4.7. And it depends on what type of uncertainty you're talking about. We'll deal with that in the lab if you're in the lab. All right, let's look at significant figures. A significant figure is just a reliably known digit. You should know all the rules for how to determine significant figures. If you don't recall them, then I have this little video. It's kind of a fun video, but it also goes over all the major rules for determining significant figures. But I like to just go through some examples to just, jog your memory, if you will. So I'm going to give a few numbers, and we'll need to write the number of sigfigs, or the number of significant figures. So, for example, with 0.1, even though we write two digits, there's really only one digit that you know. The 0 is just a placeholder, and so we can just, the number of significant figures is just 1. Now, interestingly, if you write a number in scientific notation, then all of the digits that you write it, all the digits are significant. So for example, here I would write this as 1 times 10 to the minus 1. And here I have one digit, and that is a significant figure. Here, the zeros all act as placeholders, so the number of significant figures is 2. And if I were to write this in significant scientific notation, it would be 5.4 times 10 to the minus 3, because I had to move the decimal place over 3 spots. 102, well, how many significant figures does that have? That you have to ask yourself, well, is this 0 a placeholder? And in fact, here the 0 is not a placeholder. It is a significant figure, so I have 3 significant figures. And if I write it in scientific notation, that falls out. So if I write it as 1.02 times 10 to the 2, then it shows me that there are 3 significant figures, because these 3 are all significant. Excuse me. Here I have 100.1. These are not placeholders, so there are 4 significant figures. 1.001 times 10 to the 2. Here I have how many? I have 6 significant figures, because these are not placeholders. So that's 1.00007 times 10 to the 2. And here, these zeros act as placeholders. And again, the rules are in that video, so I'm not going to go through the rules, but these zeros are placeholders. But this 0 is not a placeholder. That 0 says, you know the value for this measurement to this decimal place. You know it pretty darn well. And so the value for that at that decimal place is 0, but I'm going to record it as a 0. So this has 3 significant figures, and if I were to write it in scientific notation, it'd be 5.40 times 10 to the, negative 3. So when you write numbers in scientific notation, all the figures are significant. Now, there are some rules regarding significant figures when you're doing mathematical operations. When you multiply or divide digits, you use the lowest number of significant figures. So for example here, if I am to multiply this, if you just do this, excuse me, if you do this in your calculator, you get 410.2. All right? But when I'm multiplying or dividing, I use the lowest number of significant figures. So here, I have 4 significant figures, but here I just have 1 significant figure. So when you actually record the answer for this operation, you're just going to record 1 significant figure. That's 400. Now if I multiply these two, I get 42.075. All right, here I have 3 significant figures, here I only have 2. So when I record this answer, instead of doing 42.075, I'm just going to do 42. So when you're multiplying or dividing figures, use the lowest number of significant figures. When you're adding or subtracting values, use the smallest number of decimal places. So here I have no decimal places, and here I have 1 decimal place. So your final answer is going to have only have 0 decimal places. Now if you put this in your calculator, you get 132.7, but keeping appropriate significant figures will give you 133. And so that's the appropriate way. In this class, different people have different rules, but when rounding, we're going to do it typical. If the last digit is less than 5, drop it. If it's greater than or equal to 5, drop and round up. So for example, an 89.5 rounds up to 90. And that is true for your grade too, by the way. I'll follow that rounding. Different people have different takes on this. Sometimes people have this funny rule that if this digit is even or odd, then you round up or down if it's a 5, but we'll just do it in a standard fashion. That doesn't really come up that much. All right, and so for example here also 89.4 would round down to 89. As I said, that applies to your grade. So an 89.4 is equal to a B. Now, in general, you keep the proper number of sig figs for each step as given by your order of operations. So you'll need to remember your order of operations from high school math. So for example here, you would do the multiplication first, keeping proper sig figs, and then the multiplication and division appropriately by the order of operations, keeping the number of sig figs, and then do the addition, keeping the appropriate number of sig figs. So for example here, this 3 over 4.2, this is 0.714. All right, but 0.714, here I have 1 sig fig, here I have 2 sig figs, so this is just going to be 0.7. Keeping the appropriate number of significant figures. 2 times 6.75 here is equal to 13.5. All right, but here I only have 1 sig fig, and here I have 3 sig figs. Remember, when I'm multiplying or dividing, I keep the lowest number of sig figs. So I'm going to let this then become a 10. So this mathematical operation becomes this, 0.7 plus 10. Right? And then when I add numbers, if I add these up in my calculator, I get 10.7. But keeping the appropriate number of sig figs, when you're adding or subtracting, you keep the lowest number of decimal places. I have 1 decimal place in 0.7 and no decimal places in 10. So my answer then will be 11. Very likely that on the test you'll just have a simple question where you have to do multiple operations and express it with the appropriate number of significant figures. It shouldn't be a problem for most of you. You should have had that in high school. All right, this quick test will be in the online participation quiz soon. All right, conversion of units. You're going to be doing this like all semester, okay? And you will have some explicit questions asking you to convert units from either one system to another system, say from the British system to the metric system, or within the metric system, say from meter squared to centimeter squared or something like that. We're going to use dimensional analysis to convert units. It's pretty simple. Like for example here, say I want to convert 28 meters per second to miles per hour. 28 meters per second to miles per hour. Well, first I need to know some conversion factors. I'll provide you with most of those conversion factors. Some of them I expect you to know, like how many seconds are in an hour. Well, there are 60 minutes in an hour and 60 seconds in a minute. So in an hour, there are 3,600 seconds. In a mile, there are 1,609 meters. So a mile is approximately 4 laps around that 400-meter track. All right, so if I want to convert 28 meters per second to miles per hour, I'm going to write it out like this. 28 meters per second. And then I'm going to do some conversion factors. And these conversion factors are going to be equivalent to 1. So I'm not really changing the nature of the quantity because I'm only multiplying it by a value that's equivalent to 1. What I mean by that is, for example, I'm going to put a conversion factor here. I'm going to put 1 hour in the denominator and then 3,600 seconds in the numerator. Those values are equivalent. There are 3,600 seconds in 1 hour, so that has a value that's equivalent to 1. However, I see that my seconds are going to cancel, and it's going to leave me with hours in the denominator, which is what I want because I'm looking for miles per hour. Now, in a similar way, you can think, well, I'm going to have what in the denominator, meters or miles? Right, I'll have meters in the denominator. That's 1,609 meters. 1 mile. That cancels out my meters. So see this at dimensional analysis, just like we did with the equations earlier. And that gives me my value, 62.6 miles per hour. This brings up a good point because notice that if I were to do this appropriately, keeping sigfigs the way that we did in the multiplication or division, I would have kept the lowest number of sigfigs. And you could either say, well, I have 2 sigfigs here, or you might even say I just have 1 sigfig here. We don't consider these quantities when we're considering significant figures because we consider these quantities to be perfectly well known. So we would say that these quantities are infinitely well known. And so we don't consider them in the significant figure. So I would just consider this value, which has 3, and so I carry that over to 3. That's just sort of a good skill to have, and you'll need to do that as the course goes along. Also, we'll need to convert units with powers, and probably on your exam you'll have a question that's more akin to this, where you have to convert from one unit that has a power in it to another unit. And what I mean by power is I see this meters cubed right here. You have to do something a little more complicated. So let's say I want to convert kilograms per cubic meter to grams per cubic centimeter. So I'm going to start with 5.7 kilograms per cubic meter. I'm going to change I'm going to need kilograms here and grams here. So I need to know how many grams are in a kilogram. Remember, a kilo means 10 to the third. Right, so 1 kilogram has 10 to the third, or 1,000 grams in it. Right. And now I'll need to look at my meters. So I'm going to have meters here and centimeters here. Now remember, centi is 10 to the minus 2. These are very common metric prefixes that you'll be using all year in this semester and next, so you need to know them. In fact, you need to know all of those that I gave you earlier. So 10 to the minus 2, that means that this is equivalent to 1 over 100. That means that in 1 centimeter there is 1/100th of a meter. Or, I like to think of it as in 1 meter there are 100 centimeters. When I think of a meter, I think of 100 centimeters. All right. And hopefully you do too. So let's see. Here's my 1 meter, and that's equivalent to 100 centimeters. All right. So here, my units, kilograms, will cancel and just leave me grams. But over here, I have a problem. See, I have cubic meters over here, but over here I only have meters. So in order to make this correct, I have to cube this term. So now I have cubic meters here that cancel with the cubic meters over here. And then that's going to leave me with cubic centimeters, the appropriate units, grams per cubic centimeter. Make sure that you try this in your calculator because you have to make sure that you cube the 100 before you divide it. So make sure you get the appropriate order of operations. That's 5.7 times 10 to the minus 3 grams per cubic centimeter. All right, notice that while it looked like I only had one sig fig here, I actually had an infinite number of significant figures because that conversion quantity is infinitely well known. Okay, so I keep the lowest number of sig figs, which is just in this value. All right, let's see. I'll post a clip on Moodle. This is an audio clip, so you'll need to listen to it on Moodle. It's really just sort of for your own interest, where they talk about this guy that won the Nobel Prize and what he did in college. It's kind of interesting, but it's just sort of a human interest thing. But I'll post it on Moodle for you to listen to. So sometimes we can make up units of measurement like they did in this Smoots clip, where they just made up this unit of measurement which was based on the height of a particular person. This is our conversion factor now. We just have it sort of made up. And I want to know how many smoots is 225 meters. So I have 225 meters. Oh, excuse me. 225 meters. And I want to know how many smoots is that equal to. All right, so I say 225 meters. And then I need to make my conversion factor. So I'm going to meters here and smoots here. So I know that there are 125 meters and 364.4 smoots there. And so if I do that conversion, I get 656. And that's going to be in smoots, which again is just this made up idea. All right, we'll stop there and we'll pick up with estimates and order of magnitudes in the next